All right, this is a review of the big three algebraic physics formulas. Again, we start talking about the standard position equation, velocity equation, and then the no time equation. Let's remind ourselves that all of these are either built from a very simple principle that x equals vt. I mean, this is old school, back when you were in like third grade, that distance equals a rate times the time. That's all that's saying. And so we start out with this and we say, well, what if there's an acceleration? Well, what we did here is we said that the average velocity under constant acceleration was just some v naught plus some final velocity divided by 2. Again, this is true if we have constant acceleration. We took this, made a substitution into velocity. Then we took, well, how do you find out the final velocity? Well, this is just the basic relationship between velocity and acceleration. The velocity at any moment of time is how fast you started moving plus what you did and how long. Remember, what is an acceleration? For example, an acceleration, it's like 4 meters per second per second. Now, most textbooks are going to say that's 4 meters per second squared, but this really looks like more of a rate. It's the rate at which you change your velocity. This acceleration rate would increase your velocity by 4 meters per second, meaning every second you accelerate, you're increasing your velocity by 4 meters per second. And so if you take this 4 meters per second and multiply it by seconds, then you get an increase of your velocity. Well, if this represents delta v, then the new velocity, of course, should be what you started at plus the change in. So we get this equation. If you take these two equations together and make some algebraic substitutions, you get the position equation. And again, that's where this 1/2 at squared comes into play. This already is standard linear growth, right? V equals V naught plus AT. It's the same thing we used over here. And then the last of the big three is the simple substitution. If you look at this, this is the no time equation. It relates velocity, acceleration, and the distance, not time. These are both functions of time. X is a function of time. Some people like to think of it as x of t, and this would be some v of t. But this gets rid of time. And all we did, and I really mean all we did, was take this equation, solve for t, and then plug it into here, and then algebraically simplify, and you get something that looks like this. As a reminder, we built all of these equations based on the constant acceleration. And so if you're given a situation that does not have constant acceleration, then these three are not valid. Okay, so let's focus on these three being the big three equations and look at some of these situations. Okay, so what if we're looking at a situation where we have constant velocity? Constant velocity is implying that there's no acceleration. Well, if there's no acceleration, then we're really just doing something like this. And it really is that easy. The distance or displacement is just the velocity times the time. If you happen to have some initial position, then of course you can add that on to find the final position. Well, what if we'd have a velocity of 0? Well, if we don't have any velocity at the beginning, and let's say we don't have an initial position, then x is going to equal 1/2 at squared. Where our position, the distance we travel, is just a function of the acceleration and the time. This piece factors in the fact that we are going to accelerate for a certain amount of time, we're going to gain speed. It turns out that those are, in fact, the same thing. Okay? Well, what if we drop something? Well, if we drop something from a certain height and we want it to fall all the way to the ground, then we're still just using this equation. If we want to drop something and have to get the ground, we're going to have a final position of 0. We're going to drop it from a certain height. If we drop it, it doesn't have any initial velocity, so let's just skip that term. And then it's under the influence of gravity, and we know that gravity is going to pull you down. And so you get something like that, which if you rearrange this equation, right, just add this to the other side, you get h equals 1/2 gt squared, where this represents the time it takes to fall from a certain height if you were dropped. Now, if you were thrown down or something, well, then you'd have to have this term in it. But if you're just dropping something, you basically just get an h, right? This difference equals 1/2 gt squared. If we're dropping something, it's just a known acceleration is g. And remember, g is 9.8 meters per second squared. Again, reviewing what that means. That means that under the influence of gravity only, gravity is going to accelerate you towards the Earth at 9.8 meters per second every second, meaning you're going to increase your speed by 9.8 meters per second every second you fall. Pretty much every second you're in the air, you're going to get 10 meters per second faster towards the Earth. All right, what if we wanted a stopping distance problem? What if we were doing the car going a certain speed and you want to skid and avoid something? Well, again, this is a distance associated with some initial velocity. We want to stop. Well, that's what the beauty of this equation is. It doesn't involve time at all. If we want to stop, our final velocity is 0. Whatever the initial velocity is that your car is going, minus 2 times your brakes. Remember, the acceleration is the rate at which your brakes can decrease your velocity in that case, times some stopping distance. And so you use the v squared equation to solve a question like this. Well, if you're interested in stopping time, well, then you're going to use this equation. This equation relates how fast you are moving compared to how fast you're moving at the beginning. And let's say if you were braking, this is going to be a minus AT. So a certain speed, a certain rate, a certain amount of time, well then I'll tell you how fast you're going after you hit the brakes for so long. All of these equations are really just different versions of this. You're not going to memorize this. These are just the stories. These stories tell you things. Constant velocity tells you acceleration of 0. So we can ignore that term. Of initial velocity of 0, like we drop something, well then we can get rid of this, or this, or this. It just depends on the situation. Stopping distance implies that we want to stop, so our final velocity is 0. We're interested in the distance, so it would make sense to use this relationship. This gives you distance as a function of time, velocity as a function of time. This one relates distances. What if you wanted max height? Well, it would depend. Just telling me you want it's a max height problem, I don't know enough information. You could use the max height question. You could say, even if you were on a cliff, you could say, well, y equals some y naught plus v naught t minus 1/2 gt squared. This would be true if you started from some cliff, you threw it up, it was under the influence of gravity, and you could go ahead and graph this. If you graph this, it'd be some parabolic thing that maybe looks like this, and you could figure out the maximum height. Well, what if you had other information and you didn't care about time? Well, then you could use the v squared equation. The v squared equation could give you the same thing. That's our typical v squared equation, but if you want it to stop at the top, you're just letting the final velocity be 0. This is what you launched it at. It's going to slow down at g because we're under the influence of gravity, and this x is really just an h. And again, this would give you how far the ball goes up. Now, just as a reminder, this h is how far the ball goes up before it stops. If you were already on a cliff, then you're going to have to take that initial height and add it in at the end. So this is some h1 and this is some h2. This equation only gives you this distance. If you were already on a cliff, you'd have to add that in. Okay? This equation has the cliff height built in. So when we found this value, it is truly already the max height. Okay, what if the story said something about let's find the final velocity of something? Well, again, you could be using something like this. If you want to find the final velocity of some function of time, you tell me the rate at which you're changing your velocity, right? That is the definition of acceleration, times time, plus whatever you were going at the beginning, and I'll tell you how fast you're moving. But what if your final velocity was related to a position? Well, then your final velocity, you'd probably use the v squared equation. If you tell me you were going so fast in a car at the beginning, you accelerated, so you were going so fast, you accelerated a certain value, and you accelerated for a certain distance, and you want to know how fast you're moving at this point in space based on that distance, well then you'd use the v squared equation. It just depends, but all of these stories are still just samples of the big three. And the big three really are just these two. This is just a substitution. This is, I think, pretty obvious. It's a nice linear relationship. It's based on knowing that acceleration is literally the definition of the rate of change of velocity. And this we built from 4th grade math. This is just distance equals rate times time. We played around with a little average velocity and the velocity equation based on time, and both of those create this. These big three equations almost exclusively relate everything that has constant acceleration in 1D kinematics. Again, one-dimensional kinematics, meaning we're only looking at things moving left or right, or moving up or down. Most things moving up or down, we just replace the acceleration by gravity because we know we're under the influence of gravity. And when you're moving horizontally, it's whether you're pushing the gas on a car, positive acceleration, or you're hitting maybe a brake on something. And any of these can be negative. Right? We can have this can describe a braking or an acceleration. Same thing here. If you are going fast and you're braking, it's going to be a minus. If you're going fast and you hit the accelerator and you even go faster, well, then that's going to be a positive. Same thing here. This can be v naught squared minus or a plus. It depends on what the acceleration is. Right? If this is a plus, it means that the final velocity is greater than the initial velocity, which just means you're speeding up. If this is smaller, it means you're slowing down, and that must be a negative. So the signs kind of work themselves out. But again, these are really the big three equations, and they describe all sorts of situations. You come up with any situation you want, and you have to take a look at it. Okay, so drawing a picture, figuring out what the given information is, and kind of selects the equations. And remember, all of these equations are really just the physical relationships. We don't want to think we're good at physics because we memorize equations. Equations are bad. It's the relationships. Relationships allow you to solve the problems. Relationships will allow you to pick what formula you're going to use and why. And it just makes things easier. So these are you're not going to memorize stopping distance, use this. Max height, use this. You're going to have to think through the situation, but again, all of them boil back down to those three. Hopefully this helps you get ready for the test. Again, I would look over this. I would also watch the other video that involves some information about graphing and the calculus, and again, the calculus derivations look at situations where there is not constant acceleration.